Number 28, we are talking about a binomial experiment. And these are covered in 4.2. And here's the criteria. One thing is that each trial must be independent of the other trials. And all that means is that the outcome of one trial has no effect on the outcome of any other trial. For number 25, with a binomial distribution, we can find the mean, the variance, and the standard deviation of that distribution. And the formulas covered in 4.2, they're listed here. You need to know the total number of trials N, and then the probability of success on each trial P. And then Q is the probability of failure for any given trial, so it is 1 minus P. And you're going to use those values to calculate mean, variance, and standard deviation. And so here's the values that were listed for N, number of trials. Probability of success was 0.2, which means the probability of failure would have to be 0.8, so that those add up to 1 or 100%. The formula for mean is N times P, so we're going to do 90 times 0.2, and that is the mean of our binomial distribution. Formula for variance is N times P times Q. So 90 times 0.2 times 0.8, and there's the variance of our binomial distribution. And then the square root of the variance, that's always the definition of standard deviation. So the square root of N times P times Q gives us the standard deviation of our binomial distribution. Number 30 is about setting up and understanding a binomial situation. We have about 50% of babies born with a certain ailment recover fully. A hospital is caring for 7 babies born with this ailment. Our random variable represents the number of babies out of those 7 that recover fully. So we're going to decide whether this experiment is a binomial experiment. And so looking back at what it means to be a binomial experiment, we will see that this is a binomial experiment. There are a fixed number of trials because in our example we have exactly 7 babies. So we have 7 trials. And each trial is independent of the other trials. One baby recovering or not recovering has no effect on the health of the other babies. So each trial is independent. There's only 2 possible outcomes for each of our trials. Each of our babies either recovers or it doesn't, 2 outcomes. And we're classifying recovery as success, not recovery as failure. The probability of success of recovery is the same for each trial. It was stated that about 50% of babies recover, so success is at 50% for each of our babies. And we defined our random variable to be the number of babies that recover. So we do have a binomial experiment. Success is a baby recovering. N, our number of trials, is at 7. The probability of recovery of success is 50%, 0.5. So the value of Q, which is failure or not recovery, needs to add up to 100%. Success and failure add up to 100%. So 1 minus 0.5 also gives us 0.5 for our probability that the baby does not recover. And then the possible values that our random variable could be, and remember it is counting the number of babies that recover fully. So it could be 0 babies, 1 baby, 2, all the way up to all 7 of them recovering. In number 31, we have a binomial experiment. In our example, it says 43% of U.S. adults have very little confidence in newspapers. And so there's only 2 possible outcomes. You have very little confidence, or you actually do have confidence. And we are going to randomly select 10 U.S. adults. And we're going to find the probability that the number from our 10 that we've selected who have very little confidence is, and first of all, it's going to be exactly 5. So part A, out of those 10 we asked, what's the probability exactly 5 have very little confidence? With a binomial experiment, we always need to keep in mind our number of trials, in this case the 10 adults we're asking. The probability of success we need to know, in this case 43% have very little confidence. So what are the chances that exactly 5 out of the 10 have very little confidence? There's a formula you can use in Excel, binom.dist, for our binomial distribution. You want to put the number of successes you're looking for. In this case, exactly 5, so we want a 5 there. The total number of trials is 10. The probability of success is 0.3. And then you have to enter either true or false. If you want to know an exact number, in this case exactly 5 out of 10, you want to type false. And so this returns the probability that exactly 5 out of the 10 people we ask have very little confidence in newspapers. I'll come back to B, but I want to do C next, which said less than 4 have confidence in newspapers. So out of the 10 we asked, what's the probability that less than 4 are confident? So binomial.distribution, open the parentheses. Now, less than 4 would be the numbers 0, 1, 2, or 3. So out of our 10 adults, we either get 0, 1, 2, or 3 saying that they have very little confidence. So we actually want to enter a 3 here because we are going to do not an exact number like we did with exactly 5, but we're going to count the probability of 0 up through 3 successes. So a range here. When you're doing a range, you enter true for your last argument, and you need to make sure you're using that correct first argument here because it's counting 0 up through whatever number you enter first. So less than 4 would be 0 through 3. Now we still have 10 total adults we're asking. There's 10 trials. The probability is still 0.43, and we're typing true here. And so Excel will give you the probability back of less than 4, 0, 1, 2, or 3 adults saying they are have very little confidence in newspapers. And finishing up now with part B, it was asking an at least question. What's the probability that at least 6 out of the 10 people we ask say they have very little confidence in newspapers? So the results that could possibly fit into there are either 6, 7, 8, 9, or 10 people out of the 10 we ask say they have very little confidence in newspapers. Now Excel only has 2 options for this formula, binomial.distribution. The false option gives you the probability of an exact amount, and the true probability gives you the probability of 0 up through whatever you enter for x. So actually, before I figure out at least 6, the easiest way to do this is to first figure out the complement of that, everything not included in 6, 7, 8, 9, 10, and that would be 0 through 5, because Excel can do 0 through 5 with the formula. I would put 5 in here. There's 10 total people we're asking. Probability is 0.43, and true will give me the probability that I get a result of either 0, 1, 2, 3, or 5 people saying they have very little confidence in newspapers. So using the complement rule, if this is the probability of getting 0 through 5, then I can do 1 minus that, and that's the probability of getting 6 through 10. So anytime you have an at least and you're looking at values greater than a certain number, you need to use the complement rule if you're going to use these formulas in Excel to save you time. Number 32, we have a binomials experiment here. 78% of US adults think that political correctness is a problem in America today. So you either do think that or you don't. So there's 2 outcomes. It's a binomial situation. The probability of success is 0.78, 78%. And we're going to start off here by finding the mean of this binomial distribution. Now we need to know how many adults we're going to randomly sample, and here it says we're picking 6 adults and asking them whether they think political correctness is a problem. And so in our number of trials is 6. We're asking 6 adults. The probability that each adult would say they think political correctness is a problem is 78%. And Q, the probability of failure, was not listed, but it needs to add up to 100%. So 1 minus 0.78 gives you Q, the probability of failure. So the mean of our distribution here would be N times P, which gives you 6 times 0.78, which gives you the mean there. The variance, N times P times Q, is the formula. So multiply those values together. get the variance. And then the square root of the variance is the standard deviation. So take the square root of n times p times q, or the square root of that answer you just got for the variance, and you get the standard deviation. So enter those answers, round to the correct number of decimals, and then we're going to interpret the result. And it would be unusual for a sample to be more than 2 standard deviations away from the mean, and most samples are within 1 standard deviation of the mean. So this is asking about most samples. So most samples of 6 adults, which matches up with the calculations we just did, were for 6 trials in our experiment, would differ from the mean by no more than the standard deviation. And our standard deviation was 1.0, so they would differ from the mean by no more than 1.0.